Introduction to Mosfet. There are two major types of three-terminal semiconductor devices, that is, the metal oxide semiconductor field effect transistor, also known as the Mosfet, and bipolar junction transistor, that is BJT. Each of these two transistor types offer unique features and area of application, but Mosfet has become more widely used electronic device, especially in the design of integrated circuits, that is ICs, which are entire circuits fabricated on a single silicon chip. Compared to the BJTs, Mosfets are having more advantage. That is, Mosfets can be made quite small, that is requiring small area on the silicon IC chip, and their manufacturing process is relatively simple. The Mosfet operation requires comparatively little power, and the circuit designers have found more ways to implement the digital and the analog functions utilizing Mosfets exclusively with very few or no resistors. It is because of these properties it is possible to pack large number of Mosfets, as many as 2 billion, on a single IC chip to implement a very sophisticated, very large scale integrated digital circuit such as those for memory and microprocessors. The analog circuits such as amplifiers and filters can also be implemented in MOS technology in much smaller and less dense chips. Therefore, both analog and digital functions are increasingly being implemented on the same IC chip, which is called as the mixed signal design. Let us look into the device structure. The figure shows the physical structure of a N-channel enhancement type MOSFET. The transistor is fabricated on a P-type substrate, which is a single crystal silicon wafer that provides physical support for the device. The two heavily doped N-type regions are indicated by N plus source and N plus drain. N plus indicates that it is heavily doped. Conversely, N minus will indicate that it is lightly doped. These two regions, that is the source region and the drain region, are created in the substrate. A thin layer of silicon dioxide, as seen here, of thickness, which is represented by TOX, which we will see later, is an excellent electrical insulator which is grown on the surface of the substrate, covering the area between the source and the drain regions. The metal is deposited on the top of the oxide layer to form the gate electrode of the device, which is shown in the black. These metal contacts are also made to the source region and the drain regions as well as the substrate, and they are known as body. Thus, there are four terminals that are brought out. One is the gate terminal, the source terminal, and the drain terminal. The substrate or the body terminal is represented by B. You can see here the metal contact and the body terminal. Another name for the Mosfet is the insulated gate FET or IGFET, and this name arises from the physical structure of the device, emphasizing the fact that the gate electrode is electrically insulated from the device body, that is by the oxide layer, and it is this insulation that causes the current in the gate terminal to be extremely small. If we observe clearly, the substrate forms PN junctions with the source and the drain regions. So these PN junctions are always kept reverse biased, and the drain will always be at a positive voltage relative to the source. The two PN junctions that you see can be effectively cut off by simply connecting the substrate terminal to the source terminal. So the substrate will be considered as having no effect on the device operation, and the Mosfet will be treated as a 3-terminal device, with the terminals being the gate, source and the drain. A voltage applied to the gate will control the current flow between the source and the drain, and this current will flow in the longitudinal direction from the drain to the source in the region which is labeled as the channel region. And it is this region that has the length L and the width W, and these two are the important parameters for the MOSFET. Typically, the value of the length L will be in the range of 0.03 micrometer to 1 micrometer, and the width will be in the range of 0.1 micrometer to 100 micrometer. Another important thing to be noted is that the Mosfet is a symmetrical device, which means that the source and the drain can be interchanged with no change in the device characteristic. The figure B clearly shows the cross-sectional view of the enhancement type NMOS transistor, wherein the silicon dioxide thickness is represented by TOX, and we can see the channel region, N plus source region and N plus drain region, which indicate that they are heavily doped, and the p-type body, and we can see the 4 terminals, the source, gate, drain and the body, and this black indicates that it's the metal that is deposited on top. Next is creating a channel for the current to flow. As seen in the figure, what we have done is we have grounded the source and the drain and applied a positive voltage to the gate, which is represented as VGS. The positive voltage on the gate will cause the free holes which are positively charged to be repelled from the region of the substrate under the gate, that is the channel region, and these holes are pushed downwards into the substrate, leaving behind a carrier depletion region. The depletion region is populated by bound negative charge associated with the acceptor atoms, and these charges are uncovered because the neutralization holes have been pushed downwards into the substrate. The positive voltage also attracts the electrons from N plus source and the drained regions into the channel region. When sufficient number of electrons accumulate near the surface of the substrate under the gate, an N region is created connecting the source and the drain. Now, if a voltage is applied between the drain and the source, the current flows through this induced N region carried by the mobile electrons. The induced N region thus forms a channel for the current flow from the drain to the source, and this is called as an N-channel MOSFET or a NMOS transistor. The N-channel is formed in the P-type substrate. The channel is created by inverting the substrate surface from P-type to N-type. Hence, the induced channel is also called as the inversion layer. The value of VGS at which a sufficient number of mobile electrons accumulate in the channel region to form a conducting channel is called as the threshold voltage and is denoted as VT. And for an N-channel FET, the value of VT will be positive. The value of VT is controlled during the device fabrication, and it will typically lie between 0.3 volt to 1 volt. The gate and the channel region of the MOSFET form a parallel plate capacitor with the oxide layer acting as the capacitor dielectric. The positive gate voltage will cause the positive charge to accumulate on the top plate of the capacitor, that is the gate electrode, and the corresponding negative charge on the bottom plate is formed by the electrons in the induced channel. So a dielectric field will develop in the vertical direction, that is, this field will control the amount of charge in the channel and will determine the channel conductivity and in turn the amount of current flow through the channel when voltage VDS is applied. So that is why the name field effect transistor, that is FET. The voltage across this parallel plate capacitor is the voltage across the oxide, and this must exceed the threshold voltage VT for a channel to form. When the VDS, that is drain to source voltage, is 0, the voltage at every point along the channel will be 0 and the voltage across the oxide, that is between the gate and the points along the channel, is uniform and it will be equal to VGS. The excess of VGS over VT is termed as effective voltage or the overdrive voltage, and the quantity determines the charge in the channel, and we denote VGS minus VT to be equal to VOV, where VGS corresponds to the voltage that is applied to the gate, VT corresponds to the threshold voltage, and VOV corresponds to the overdrive voltage or the effective voltage. Now some of the parameters that are required in order to compute the numericals, one is the oxide capacitance, that is COX, which is given by EOX divided by TOX. EOX corresponds to permittivity of the silicon, and this is equal to 3.45 into 10 to the power minus 11 farad per meter. Basically, this COX corresponds to the oxide capacitance, and it is the capacitance of the parallel plate capacitor per unit area, which is measured in units of farad per meter square. TOX corresponds to the oxide thickness, and it is determined the process technology which is used to fabricate the Mosfet. Sometimes we can also represent the capacitance in the Mosfet in terms of femtofarad, which is equivalent to 10 to the power minus 15 farad. Next is the product of the process transconductance parameter, which is given by Kn dash, and the transistor aspect ratio W by L, which is the Mosfet transconductance parameter Kn. So we have Kn to be equal to Kn dash into W by L. This Kn dash corresponds to the product of electron mobility, that is mu n, and oxide capacitance COX. And this parameter Kn dash is determined by the process technology used to fabricate the Mosfet. The Mosfet parameter Kn has the dimensions of ampere per voltage square. One more important thing to be remembered is that W by L ratio, which is the aspect ratio, is a dimensionless quantity and is determined by the device designer, and the values of W by L or W and L can be selected by the device designer to give the device IV characteristics as per requirement. But for the fabrication process, we will have something called as the minimum channel length, which will be represented as L minimum. Next is the circuit symbol of the N-channel enhancement type Mosfet. If you observe in the figure A, the spacing between the two vertical lines that represent the gate and the channel, it indicates that the gate electrode is insulated from the body of the device. The polarity of the P-type substrate, that is the body, and the N-channel is indicated by the arrowhead on the line representing the body. And this arrowhead will also indicate the polarity of the transistor, that is the N-channel device. Because Mosfet is a symmetrical device, it is often useful for the circuit design to be designated with one terminal as a source and the other terminal as the drain without having to write S and D besides the terminal. So in the figure B, we have placed the arrowhead on the source terminal, distinguishing it from the drain terminal. And this arrowhead points in the normal direction of the current flow, and it will indicate the polarity of the device, that is the N channel. And the drain is always positive relative to the source in the N channel FET, which is clearly indicated in this particular symbol. But if we want to have a further simplification of the circuit symbol, then we can see the one which is represented in the figure C. And this symbol is used in applications when the effect of the body on the circuit operation is not important. So in most of our explanation with regard to the biasing of the MOSFETs, we will be representing the circuit symbol as shown in the figure C. So to be very brief, I have tabulated conditions and the formulas for the operation of the NMOS transistor in each of the three possible regions, that is the cutoff region, the triode region and the saturation region. If we want to operate the MOSFET as a switch, then we need to operate the MOSFET in the cutoff region and in the triode region. Whereas on the other hand, if we want to design a MOSFET as an amplifier, it must be operated in the saturation region. In most of our topics that we are going to discuss, we are talking about MOSFET which are used in amplifiers, so we will be more interested in using the MOSFET in the saturation region. Tell you the boundary between the triode region and the saturation, which is determined by whether VDS is less than or greater than the overdrive voltage at which the transistor is operating. So an equivalent way to check for the region of operation is to examine the relative values of the drain and the gate voltage. So to operate in the triode region, the gate voltage must exceed the drain voltage by at least VTN volts, that is indicated here, which ensures that the channel remains in the continuous and is not pinched off. On the other hand, when it is operated in the saturation region, the channel must be pinched off at the drain end, and this pinch off is achieved by keeping VD higher than VG minus VTN. That is, not allowing VD to fall below VG by more than VTN volts. So graphically it is being represented here. You can see VD is less than VOE, that is the drain to source voltage is less than the overdrive voltage, and here drain to source voltage is greater or equal to the overdrive voltage. This ID versus VGS characteristics shows that in the saturation region the drain current constant and it is determined by VGS or VOV, that is overdrive voltage, and it is independent of VDS. So that is, what that implies is that the MOSFET operates as a constant current source where the value of the current is determined by VGS. So in effect, the MOSFET operates as a voltage controlled current source with the control relationship which is described in these two equations. This relationship underlines the application of the MOSFET as an amplifier which is non-linear. And if we want to design linear amplifiers, then we need to obtain non-linear control or the transfer characteristics, because it is possible to obtain linear amplification from the non-linear control or transfer characteristics. So if we observe the ID versus VDS characteristics, and if this characteristics is extrapolated, then they will intercept the VDS axis at the point VDS is equal to minus VA, where VA is a positive voltage. And if the value of ID is equal to 0 at VDS, then VA will be equal to 1 by lambda, where VA is the device parameter with the dimensions of V, and for a given process VA is proportional to the channel length that the designer will select for a Mosfet. So the device parameter is computed as VA is equal to 1 by lambda, and lambda is inversely proportional to the length. And one more important parameter that is required for us is the output resistance, which is given by R0 and which is equal to device parameter divided by ID, that is the drain current. And the inverse of the output resistance will give us the value of the slope. So in this particular tutorial, I have focused mainly on the enhancement type Mosfet, that is N type. That is because our interest is to study the Mosfets as amplifiers, wherein we'll be using the enhancement type N channel Mosfets. Thank you for watching.